Welcome to projective geometry, where certain figures in high dimensions can be projected down onto low and lower dimensions. Now don't go fall asleep, gonna need your full attention. Imagine you were standing in a room looking up at the ceiling. That's right, you know what's up. If you move your head, you will be able to see every point on the ceiling that there can be. Now imagine the ceiling was infinitely large. With 20/20 vision, you could see really far. You would have a clear line of sight on every point of the ceiling. You feel me now?
Stratified.
You're standing now with your head down at the origin of R3. That's 3D. You got 3D lines of vision. Those vision lines all originate at the origin, while the ceiling is z equals 1 in the orange ink. Every point on the plane z equal to 1 has a unique line of vision begun. Well, line of vision from the origin close to none projects on a point unique on the plane above. Since each line for the origin is half above, half below, this half space above equals the half space below. It's like a ceiling above you and a floor down low, where there's a mirror that reflects everything down below, yo. But some lines of vision don't match the points in the plane. In your hypothetical room, if you look straight, you won't be looking at points on the ceiling above, nor looking at points on the ground or thereof. So where did the lines lead? Where do the points read? Any line on the plane of z equal to naught won't cross z equal to 1 at spots on the plot. Now what could these points possibly represent? Well, suppose you are watching just one among them, a ceiling that moves away from you. Your line of sight moving lower till the point's out of view. Here in the limit, you are now looking straight. The points represent infinitely far away. In LaTeX lingo, they're at /infinite. There's one catch though, that we ought right now to make plain. Since each other line creates a point in the plane, these lines too make a unique point in infinity. So, in other words, looking straight in one way is the same as checking your 6, okay? Now this fact may cause you some level of dismay, but fret not, for things work out better, one could say. These points that are on the classical 2D plane combine with points at infinity to form an extended plane, which the mathematicians call real projective plane. We're sincerely sorry for making this rhyme quite lame. Now points on the projective plane are lines in space. These are prescribed uniquely by their direction. Use a vector ABC to put them in place, scale up and down, get all points without rejection. Now what point is ABC on the plane, you plead? To scale it to z equals 1 and you will see that the point goes to A by C and B by C, while C, when not, is a point at infinity. Next question, what becomes of a line in R3? A line has many points, don't need a PhD to find a span of lines that lie flat in 3D. It will just end up becoming plane, you see? Now what will this thing even look like well, you're gonna see. It's a simple relation. The plane for line ax plus by plus c equals naught is ax plus by plus cz equals 0, as thought. Z equals 0 is a plane seeing points far away. It's the collection of points at infinity, hence forming a line in infinite vicinity. Let's move on to the concept of duality. Now here's an interesting proposition. There's a duality that holds in the third dimension. For every plane that rests upon the origin has a unique normal line with the same beginning. When ax plus by plus cz is naught, the normal vector can be confirmed by the dot to be just the direction ABC which ought on the projective plane hit a unique spot. Every line ax plus by plus c equals 0 has a dual point a over c, b over c, no? Properties that become reflected as you go. A point through lines duals the line of dual points is so. Let's say you want to find where two lines come to meet. Gauss-Jordan matrices, time will soon deplete. Instead consider the line that lies where planes complete. It's normal to both normal directions, quite a feat. Now how to find this normal of normals, you ask? Well, the cross product comes readily to the task. Arrange your equations in tidy little stacks. The formula is simply Kramer's rule in a mask. Now to 2 points, what line must we designate? Simply find the plane through the lines that correlate. Cross again with 1 as the third coordinate, and well, there's your line, with nothing inordinate. Projections show conic sections in a new light. Imagine the cones project as lines of sight onto our good old plane of z equals 1, as they might. All shapes of conics will get an equal fight. But first, welcome a new player. The unit sphere. Lines of sight, 2 points of intersection appear. One in upper and one in lower hemisphere. A floor mirror replaces the lower point here. Cones intersect the sphere it circles, quite tame. The cone's equation's difficulty deserves some fame. Instead, cylinders too fit the circular frame from which the circle's equation we may reclaim. One final step we need, homogenization. The equations must be scalable to use projection. Sphere equates sum of squares to unity perfection, multiplying results in the cross-sections equation. Now how do these different shapes categorize? For circles, the cones must point up into the skies. Parabolas touch z is not, ellipses capsize, and hyperbola? That's left as an exercise or size. Projective geometry comes up in other places. The projective complex plane is one of those cases. Complex solutions of elliptic curve equation form a deformed torus on every occasion. It's like the solutions of conic sections on a sphere would map to a circle, as here it appears. This gives rise to what we call the genus of a curve, and interesting consequences are therein served. These sorts of curves will come up in cryptography, and to the proof of Fermat's last theorem, they're key. As to algebraic geometry from Italy, but that's for next time. For now, we'll drop the beat. Peace.